Okay, so now we are very happy to have Sungjay from KIAS. He's going to tell us about emergent supersymmetry on the edges. Okay, please start.
Thank you. I'd like to begin by thanking the organizers for this opportunity to give a talk at this workshop. It's always my pleasure to be in Kyoto, at least in this time online. So today I'm going to talk about this emergent supersymmetry on the edges. This talk is based on my let's see whether my pointer is working. Joint work with Jimbom Bae, who is now at Oxford. And you can find the archive number here. So let me start. So whenever you have a question, please interrupt me. Wait, what happens? Oh, okay. All right, so let me first briefly review, start with some brief review on the quantum Hall effect. Well, this is basically a system of electrons moving around the two-dimensional plane. And we also turn on some magnetic field perpendicular to these two-dimensional planes. And in this system, we can define the so-called Hall conductivity, which is given by these expressions, where mu is the filling fractions. Originally, we observed the integer values for these filling fractions, but subsequently, we also observed the fraction numbers for these filling fractions, such as 1/3 and 2/5, and so on and so forth. And one remarkable fact about this quantum Hall effect is that we have charged particles moving around these two-dimensional systems, but this charged particle is now carries a fractions of charge and spins, although these electrons are indivisible constituent of the matters. And we believe that this is a consequence of the strong interactions between electrons. And that's the reasons why this quantum Hall system is important and interesting. And today, instead of studying the microscopic description of this quantum Hall system, let me focus on the macroscopic descriptions. In other words, the low energy effective theories. So suppose that we start with a certain systems, which is in the fractional quantum Hall phase. This is basically three-dimensional gapped phase. So the low energy effective theory can be described by the topological field theories. And one of the simplest and the prominent example of that is the U1 Chen-Simon theories, which is given by these expressions. So here, the small a mu is an emergent dynamical gauge field. This is different to the electromagnetic field. Rather, this electromagnetic field is now regarded as a background gauge field and denoted by the capital A mu. And these are the, there are two terms in the Lagrangian. The first term is nothing but the Chen-Simon's coupling for this dynamical gauge field, where K, the Chen-Simon's level, is now quantized. And we have another term, which basically the coupling between the electromagnetic field and the topological current. And this model has been generalized to many different ways, such as the n copies of the U1 Chen-Simon theories with non-trivial K matrix, or the non-abelian Chen-Simon theories. Of course, for the non-abelian Chen-Simon theories, it's very difficult, it's quite non-trivial to write down the coupling between the electromagnetic field and the non-abelian Chen-Simon field. But today, let me just skip the part. And today, I'd like to focus on this first term. So in this low energy descriptions, the charged particles or anyons can be described by the pseudo particles, namely the Wilson lines. So for instance, let me consider this U1 Chen-Simon theory again. First, in order to avoid some subtleties related to the spin structures, let me consider the case where the Chen-Simon's levels are given by even integers. So in this case, the Wilson line can be described by these expressions, where we have two parameters. C is the contour that this pseudo particle is wrapping around, and there is another parameter, small n, which refers to this U1 gauge charge. And from the statistical phase, you can read off the spin of this Wilson line, which is given by n squared over 2k modular integers. And we can also show that this U1 gauge charge is now subject to the periodicity conditions. This is because the expectation value of this particular Wilson line, WK, is always trivial. Therefore, the Wilson line Wn and Wilson line Wn dressed by this WK are equivalent. And due to these periodicities, we have finitely many different Wilson lines in this Chern-Simons theories. And then let me discuss about the Chern-Simons theory on a manifold with boundary, where we have the so-called the famous bulk boundary correspondence. So in the bulk, we have the GK Chern-Simons theories. The gauge group is G, Chern-Simons level is K. And we can argue that on the boundaries, there are edge mode, and whose dynamics is now governed by the chiral part of the Westermüller-Witten models. And as I explained you in the previous slides, we have Wilson line in the bulk, whose spin is given by S. And that Wilson line now corresponds to the primary state in this Westermüller-Witten models, whose conformal weights are given by the spin of the Wilson line. And we have a finitely many different Wilson line. Similarly, on the boundary, we have a finitely many different primary state because this Westermüller-Witten model is a rational conformal field series. In the bulk, we have the so-called one-form global symmetries, which can correspond to the center global symmetry of this Westermüller-Witten models. And then let me present the goal of today's talk. So today, I'm going to show you that there are certain fractional conformal systems which have emergent supersymmetry current on the boundaries. And via this bulk boundary conditions, this claim is the same as the following claim. There are certain chiral Westermüller-Witten models which become supersymmetric. More precisely, I'm going to show you that when Chern-Simons theories, those Chern-Simons theories are placed on the manifold here in the bulk, we can see that there are supersymmetric current on the boundaries. This is quite interesting because, as all of you know, we haven't discovered any space-time supersymmetry in nature yet, such as the collider experiment. But if we can find the materials or some condensed matter system which realize this fractional quantum Hall system, maybe we have a chance to detect the supersymmetry in nature. But in what sense do I mean the emergent supersymmetries on the boundaries? But to answer that, let me first remind you the following fact. The Tricritical Ising model is supersymmetric. When I first learned about this fact, I got a little puzzled because the Tricritical Ising model is a bosonic conformal field theories. Therefore, the spectrums in this models has no operator of half integer spins. There is no fermionic operator at all. Every operator carries integer spins. Therefore, this model cannot have any supersymmetric current. So more precisely, this tricritical Ising model can be usually described by the Virasoro minima models at central charge 7/10. This model has 6 chiral primaries, the representation with respect to the Virasoro generator, left moving or right moving, whose conformal weights are given by 0, 1/10, 3/5, 3/2, 3/80, and 7/16. And let me denote the corresponding character as chi sub h, where the subscript h refers to the conformal weight of the corresponding primaries. So using these conformal characters, we can construct the modular invariant partition functions, which is given by these expressions. And from these torus partition functions, we can read up the spectrum of the given theory, the tricritical Ising models. And for instance, this one will correspond to the identity operators. This one these three will correspond to so-called the thermal field operators. And the last two will correspond to the spin field operators. And as you can see, none of those operators carries half integer spins. All of them are scalar primaries, and the descendants can carry integer spin only. In other words, this tricritical Ising model or Virasoro minimum models has no operator of spin 3/2. Therefore, there is no supersymmetric current at all. Then why do people say the tricritical Ising model is supersymmetric? Well, to see that, let me first note that in this tricritical Ising model, we have the scalar primary denoted by epsilon 2 prime of scaling dimension 3. And this is the Virasoro minimum models. So basically, we know everything, including the operator product expansions of this particular operator, epsilon 2 prime, which is given by these expressions. And as you can see, this OP can factorize into two pieces, the holomorphic part and the anti-holomorphic part, where this holomorphic part involves the stress energy tensor, and this number is the same as the central charge. So you can see that in this OPE, the only identity operator and its descendant are involved in this OPE. And that factorization implies that the chiral part or holomorphic part of this operator, the scalar primary epsilon 2 prime, which I want to denote by epsilon 2 prime of C, of conformal weight 3/2, would satisfy the holomorphic OPE, which is given by these expressions. And that is nothing but the n=1 superconformal current OPE. So that implies that the chiral part of the tricritical Ising models, which surely contains this epsilon 2 prime of C, has the n=1 superconformal symmetries. However, this chiral part itself is not a genuine two-dimensional series due to the gravitational anomalies. So based on this observation, let me rephrase the goal of today's talk. Today, I'm gonna search for the non-chiral Westerminer-Witten models, which contain a scalar primary or a scaling dimension 3s, which satisfy very special form, the very special OPE. The OPE can factorize this into two pieces, where the holomorphic part is the same as the superconformal current OPE. If that happens, then the chiral part of those non-chiral Westerminer-Witten models has a supersymmetric current G, and that supersymmetric current G can be understood or identified as a holomorphic part of this operator O. In other words, I'm gonna show you that these are the Westerminer-Witten models having the very operators O. However, unlike the Virasoro minimum models, it's very non-trivial to compute the OPE in an interacting bosonic CFTs. So we need to think about alternative approach to attack these problems. And I'm going to show you that the Jordan-Wigner transformations will play a crucial role for this alternative approach. And this Jordan-Wigner transformation is also known as the bosonizations and the fermionizations. So any questions so far? All right, so if not, let me proceed. So in order to motivate ourselves to make use of this Jordan-Wigner transformations, let me consider this tricritical Ising model example again from a different angle. For that, let me first remind you that at the same central charge, 7/10, we have a different series, which is the n=1 supersymmetric minimum models. This is different to the Virasoro minimum model, this is a fermionic theories by definitions. And as all of you know very well, in order to define the fermionic theory on a manifold, we first need to specify the spin structures. For instance, on the two torus, we have 4 different spin structures: NS-NS, RNS, NSR, and RNR. And the corresponding partition function will be denoted by CNS, NS tilde, R, and R tilde for convenience. Unlike the bosonic CFT, those partition functions are not invariant under the SL2G transformations. Instead, as you can see, this NS-NS partition function will be invariant under the S transformation, which is one of the generator of this modular transformation group. But this partition function will map to RNS partition functions on the T transformations. Similarly, this partition function RNS can be mapped to NSR partition functions on the S transformations, and NSR transformation and NSR partition function will be invariant on the T transformations. And the Ramon partition function will be invariant under the modular transformation group. And for this n=1 supersymmetric minimum models, interestingly, we can show that their partition functions can be expressed in terms of the tricritical Ising model characters as follows. For instance, this chi sub 0 is the vacuum character for the Virasoro minimum models or tricritical Ising models. And this is the character for the primary state of component weight 3/2 in this tricritical Ising models. And there are a couple of comments I'd like to make here. The first thing is about this NS-NS partition functions, which is given by these expressions. And let me first focus on the first term here, which can be understood as a super Virasoro vacuum character. When you expand it, you have the following 2 terms. And these 2 terms will correspond to the supersymmetric current, G and G bar, in this supersymmetric minimum models. And then I would like to remind you that this chi 0 will correspond to the identity, and chi 3/2 can be correspond to epsilon 2 prime of Z, which was identified as a holomorphic part of the epsilon 2 prime. This operator, the scalar primary of scaling dimension delta 3, which I explained in the previous slides. So from these expressions, we can see that this epsilon 2 prime of Z, the holomorphic operators, actually appears as the supersymmetric current in these supersymmetric minimum models. And this chi 3/2, the character of this Virasoro minimum models, appears as the super Virasoro vacuum descendant, as you can see here. And the second comment is about this Ramon partition functions, which now vanish for these examples. Well, for supersymmetric theory, actually these partition functions can be understood as an index. So we have only constant value. But now we have this constant value becomes zeros. And there are 3 possibilities to explain this vanishing Ramon partition functions. A, there will be no supersymmetric vacuum in the Ramon sectors. In other words, the supersymmetry is spontaneously broken. B, the number of the bosonic supersymmetric vacua is now same as the number of the fermionic supersymmetric vacuum. Therefore, we have perfect cancellations between the bosonic state and the fermionic state. And the last possibility, which can explain this vanishing Ramon partition function, is related to the free fermions. This is because because when we have this free fermion on the 2-dimensional plane, to the 2-dimensional torus, subject to the periodic boundary condition along any cycles on 2 torus, we can have a fermionic zero mode. And that fermionic zero mode make this Ramon partition function to vanish. But for this n=1 minimum models, supersymmetric minimum model at central chart 7/2, we can show that the A will explain the origin of this vanishing Ramon partition functions. So why is that? Well, to see that, let me first remind you, let me first explain the supersymmetric unitarity conditions. So let me consider this anti-commutation relation between the superconformal charge, G, which is proportional to L0 minus C over 24. And because of the unitarities, it has to be non-negative. In other words, the conformal weight in the Raman sector in the supersymmetric theories must be greater than or equal to the central charge over 24. And this equalities happens when the given theory has a supersymmetric vacuum. For this n=1 supersymmetric minimum model, we can read off this Raman conformal weight from this particular partition function, the NSR partition function, which is given by these expressions. From that, we can see that the conformal weights are given by 3 over 80 and 7 over 16, which is strictly greater than C over 24. Therefore, the supersymmetric minimum model does not have any supersymmetric vacuum. In other words, the SUJI is spontaneously broken in the Raman sector, and that explains why the Raman partition function should vanish. All right, so then one can naturally ask the following questions. What's the relation between this bosonic critical Ising models and this n=1 supersymmetric minimum models? Actually, those two theories are mapped to each other via the generalized Jordan-Wigner transformations, which is also known as the bosonizations and fermionizations. And as I explained in the previous slides, the supersymmetric current in the supersymmetric theory, G, can be identified as a holomorphic part of the epsilon 2 prime operators satisfying this in OPE. So based on these observations, let me rephrase the goal of today's talk again. So today, we're gonna search for the fractional quantum system which has a supersymmetric current on the boundaries. For that, we're gonna search for the bosonic Westermüller-Witten models, which has a scalar primary operators of scaling dimension 3s, satisfying this very special OPE. However, this is very difficult problems. So let me translate this problem into another form. Today, I'm gonna search for the bosonic theory B, which can be mapped to the supersymmetric theories via the Jordan-Wigner transformations. If that happens, in other words, if we can find such a bosonic theories, we can argue that the supersymmetric current in these fermionic theories can be identified as a supersymmetric current on the boundary of this fractional quantum system corresponding to these bosonic theories. So any questions so far? This is the basic idea of the today's talk.
Excuse me, can I ask?
Mm-hmm.
So what kind of pure chance-Simons gauge theory shows supersymmetry on boundary? So all the gauge group or?
No, very special, only these.
Oh, I see.
Yeah, these are the things I want to explain today.
And another question is about pure bosonic chance-Simons gauge theory can be promoted to a supersymmetric one by introducing auxiliary fermion inverter, right? So and after doing that, we can introduce boundary on the manifold, and then maybe I guess it's possible to construct a supersymmetric or a boundary theory including fermionic degrees of freedom. So,
but none of, I mean, not all of them.
These two constructions are the same, or you are talking about different?
I would say it's a little different because those are supersymmetrizations in the bulk can be done for any gauge group, any Chern-Simons level.
Yeah.
But what I want to talk today is for in order to realize this system, we have to choose very special group and the Chern-Simons level. So I think those two approaches will not be the same. Can I answer your question?
Can I further ask along the same line?
Yes.
Yeah, that's true because you have only special cases that shows this behavior, but end
Right.
result on the boundary. Do you know whether end result is different?
What is the end result here?
When you start with supersymmetrized Chern-Simon and go to boundary, or just start with bosonic theory and extract the supersymmetric boundary theory. So those are two endpoints. And I'm just asking whether two endpoints are clearly distinct in terms of their content and stuff.
I guess so, because when you supersymmetrize the bulk theories, this is not the low energy effective action in a sense, because we can further integrate out the auxiliary field and end up with the bosonic Chern-Simon theory in
With different
the bottom.
level.
Yeah, and we are today we are focused on this the lowest physics, a lowest energy scale, and in that low energy scales, we are in order to have the supersymmetric current in that lowest energy scales. I guess we need to choose very special gauge group and the Chern-Simon level. Does that answer to your question?
I guess I could further than ask. I understand what you just said. So as you say, you can choose to remove the heavy guys and end up with a Chern-Simon theory with different shifted level.
Yes.
Right. So I guess comparison would be the supersymmetric theory before that integration out and then go to the boundary. And after you integrate out and have this shifted Chern-Simon level and go to the boundary.
Boundaries, yes.
Yeah, are they same or are they different?
Are you asking whether these two processes will commute or not?
Yeah, I guess so.
I guess they commute. But yeah, let me think more.
Thank you.
Yes. More questions?
Yeah, hi. I have a question. So, you know, this is a naive question. I just want to understand something. So, are you saying that only certain filling fractions will support supersymmetry?
Oh, yes.
What is so special about those particular filling fractions? I mean, I don't know which ones, but
because so let me go back to that question later. Is that okay?
Okay, sure. Thank you.
So in a short answer is that if you choose arbitrary gauge group and Chern-Simon level K, you do not have any H mode which can carry the spin 3/2. So we need to choose very special group and level so that the boundary can have H mode of spin 3/2. But let me go back, get back to that. Let me talk about that later in this talk.
Oh, sure. Thank you.
Excuse me, I have one question.
Right.
In this slide, so you showed Witten and the Chern-Simon correspondence in the left-hand side. And so now you ask a question whether a supersymmetry appears on the boundary for Chern-Simon theory in the bulk. And so to find supercurrent, so you consider you apply the Jordan-Wigner transformation to the bosonic theory on the boundary, and so you end up with some Fermi-Naive theory, right?
Right.
So you I think you are claiming that if the Fermi-Naive theory has supersymmetry,
yes,
so then the original Chern-Simon theory can have supersymmetry at the edge.
Right.
I see. So, but I wonder if the Jordan-Wigner transformation. So what's the role of Jordan-Wigner transformation here?
The role of is that so originally, let me so here this is the Tricritical Ising model. Let me take this example again. And as I tell you, the chiral part has a supersymmetry here. Try to get the Ising of this. And the Jordan-Wigner transformation will map this tricritical Ising model to n equal 1 Suji minima model, right? And in order to understand this part, we need to show that this theory has this particular OP operator which satisfies this OP, right? If you can find such a bosonic theories, we can say that the chiral part will have a supersymmetric current. But the problem is that for the Witten model, for instance, we can easily see that whether or not the given theory has scalar primary of scaling dimension 3, but it's very difficult to compute the OP in general. It's an interacting CFT, and even though it's a rational conformal field theory, it's not easy at all to compute the OP of that particular primary operators. So the Jordan-Wigner, the reasons why I want to apply Jordan-Wigner transformation is that forget about this OP for a moment. And if you apply the Jordan-Wigner transformation to the bosonic theories, then you obtain the fermionic theories. When this fermionic theory is a supersymmetric, then we can argue that the original bosonic theory should contain this operator satisfying this OP without any computation. That's the reasons why I want to use the Jordan-Wigner transformation. Does that?
Yeah, but in the original bosonic theory, I wonder if the Suji current is in the untwisted sector. So is it in the untwisted sector or twisted sector?
Untwisted sector is in chiral part. Yeah. The original non-chiral theory does not have any supersymmetric current. Of course, it's a bosonic theory.
Right.
Yeah. But the scalar operator satisfies this interesting OP.
Okay, thank you so much.
More questions? If not, let's move on. But what happens here? Something stuck. Sorry. I'm sorry. My program doesn't work. Let's see. Okay. Oops. How can I erase this? Wait a second. Do you know how to erase this annotation stuff?
Yeah, there should be a button for clearing.
Okay, let me first stop sharing and let me share the screen again. This is the way how I can solve the problem.
Sure.
All right. So those, okay, great. It's clear now. But there's one more problem. Actually, it's rather non-trivial to construct the supersymmetric current in a given fermionic theory as well, in an interacting theories. Instead, I'm gonna search for the fermionic theories which satisfy those 4 conditions instead of constructing an operator G and showing that G satisfies the one supersymmetric current OP. So I would like to call those conditions the necessary supersymmetric conditions. And once this fermionic theory satisfies those conditions, I would propose that this fermionic theory is supersymmetric. So the condition 1 is that the NS partition functions should be written as the following form. So this chi3/2 is the chi3/2 that appears in the corresponding bosonic series. And here the important thing is that this operator, this one, should appear as the vacuum descendant. Otherwise, the spin 3/2 cannot play a role as a candidate for the supersymmetric current. So this is the condition 1. The NS partition functions of the fermionic theories you can construct from the bosonic theory via Jordan-Wigner transformation must have the following term. The second condition is that the Raman sector spectrum, the conformal weight H, must obey the following the lower bound, C/24. As I explained in the previous slides, for the supersymmetric theories, this can be understood as a supersymmetric unitary conditions. And the third condition is the following. The Raman partition function of this fermionic theory must be given by constant values. Again, this is because for the supersymmetric theories, these partition functions should play a role as an index. Finally, all these partition functions should allow the supervirtual character decompositions. But to be honest, actually the last condition is very weak. Even for the non-supersymmetric fermionic theories, sometimes the partition function can allow the supervirtual character decompositions. So this condition is quite weak, but the upper three conditions play a quite will constrain a lot for the constraint, will introduce a very strong constraints. So once this fermionic theory satisfies those conditions, I would propose that this fermionic theory is supersymmetric. So this is the basic idea how I attack the problems. I'm gonna search for the bosonic theories which can be mapped to the fermionic theories satisfying these conditions. If you can find such a bosonic theories, we can say that the corresponding Chern-Simons theories will have a supersymmetric current on the boundaries. All right, so that's the reason why I want to use the Jordan-Wigner transformations. So let me give you some short review on the Jordan-Wigner transformations. And due to the lack of time, let me just skip the traditional Jordan-Wigner transformation developed by Jordan-Wigner in 40 or 50 in the spin chain system. Let me just introduce the modern perspective of the Jordan-Wigner transformations. And for that, let me start with the bosonic theories with a non-anomalous G2 symmetries. This is quite important. This bosonic theory must have the G2 symmetries. And then we can relate the partition function of the bosonic theories and the partition function of the fermionic theories on any Riemann surface of genus G as follows. So let me first explain what each letter actually means. The rho is the spin structures on the Riemann surface sigma G. And small s refers to the G2 gauge field. And the capital T is the background G2 gauge field. So here the G2 symmetry of the fermionic theories can be understood as a -1 to the F. But still we have a bunch of extra terms here. The last term, we have a cup product, which is basically the same as the wedge product in a sense. And then let me discuss about these terms, which is known as the off invariant. This is basically multi-index of the Dirac operators, which count basically the fermionic zero mode on a given Riemann surface. For instance, on the two torus, this off invariant become 1 for this particular spin structures and 0 for other spin structures. This is because, as I explained before, the free fermion can have fermionic zero mode only when it is subject to the periodic boundary conditions. For the other spin structures, the fermion cannot have fermionic zero mode. Therefore, this off invariant becomes zeros. And these things, the exponential of I pi off invariant actually arises as a partition functions of the Kitaev spin chain in the non-trivial phase. So here, this Kitaev spin chain is the gap system, and the theory has this G2 symmetries. Then this Jordan-Wigner transformations, this one, implies that the fermionic theories we would like to construct can be understood as follows. So we first, so we start with the bosonic theory coupled to the Kitaev spin chain and quotient those systems by the diagonal G2 subgroup of these two. So this is the way how we construct the fermionic theories. And from these formulas, for instance, in the tutorials, we can relate the fermionic partition function on the left-hand side to the twisted partition functions of the bosonic theories on the right-hand side. And from that, you can see that the spectrum of the bosonic theories and the spectrums of the fermionic theories are related as follows. So in the bosonic theory, in the untwisted sectors, we have these spectrums, and twisted sector spectrums are this. And from this table, you can see how each Hilbert space can be mapped to each other's. And we would like to call it as a dualities in a quotation mark. From these pictures, you can see that the fermionic state actually arises in the twisted sector of the bosonic theories. In fact, this is quite well known in the well-known example, which is the massive Turing models, and the duality between the massive Turing models and sine-Gordon models, where the fermionic state can be arises as a domain kink solitones in other theories, which is the spectrum in the twisted sectors. All right, so this is the basic of the Jordan-Wigner transformations, and I'm going to show you that only these models can be mapped to the supersymmetric theories, which satisfy the condition that I explained before via the Jordan-Wigner transformations. To be more concrete, let me work out some examples. So the first example is SU12, level 1. This is the central charge 11 bosonic rational conformal field theories, whose partition functions can be written as follows. And as you can see, there are 12 chiral primaries. And in this table, I summarized the component weight of those chiral primaries. And these bosonic theories has G2 symmetries, which is the subgroup of the center symmetries. And you can easily read off the G, and here I summarize how this G2 symmetry will act on each these primaries. So based on this data and applying the Jordan-Wigner transformation to bosonic theories, we can construct the fermionic theories in correspondence. So for instance, the NS partition function of this fermionic theories can be written as follows. And you can see that the chi sub 6, whose conformal weight 3/2, indeed appears as the descendant of the NS vacuums. So these fermionic theories satisfy the first conditions. So, and this one can play, it becomes a candidate for the supersymmetric current. Then let me take a look at this NSR partition functions, from which we can read of the Ramon conformal weight. From this Jordan-Wigner transformation, we can show that it is given by these expressions. And from this expression, we can read off the Ramon conformal weight, which are given by 11/24 and 9/8. And you can see that this is greater than and equal to the central charge over 24. And this Ramon vacuum actually saturate this unitarity bound. So this fermionic theory satisfies the second conditions. And finally, the Ramon partition function of this fermionic theories is given by the constant number, 288. So it behaves as an index. And these two results the fact that this Raman vacuum saturates this lower bound, and we have non-zero constant values for this Raman partition function are consistent with each other. So from based on these observations, we can propose that this fermionic theory we construct, we can obtain from this SU12 level 1 theory is supersymmetric, and the Raman vacuum preserve the supersymmetries. Therefore, if we place this SU12 level 1 Chern-Simons theory in the bulk, we have a supersymmetric current on the boundaries. So this is the one class of these theories which preserve the supersymmetries. Let me work out one example in this class. For instance, E7 level 2. This is a central charge 133/20 bosonic CFT, whose partition function is given by these expressions. We have 6 chiral primaries whose conformal weights are summarized here. Again, this E7 theory has a G2 center symmetries, and their actions on each primaries are summarized here. So based on that, we can compute NS partition functions and NSR partition functions and Raman partition functions. And as you can see in this NS partition functions, this chi1, which is the conformal character for 3/2, appears as a descendant of the vacuum. So it can play it becomes a candidate of the supersymmetric current. And from these partition functions, we can read off the conformal weight in the Raman sector of these fermionic theories, which is 21/16 and 57/80, which is strictly greater than the central charge over 24. So if this fermionic theory becomes supersymmetric, that fermionic theory wouldn't have any supersymmetric vacuums. And indeed, when you compute the Raman partition function of this fermionic theories, we have 0. Therefore, these two results are consistent to each other. So in other words, this fermionic theories we can construct from this E7 level 2 is supersymmetric, but in the Raman sector, the supersymmetry is now spontaneously broken. So therefore, when you have E7 in the bulk, on the boundary, we have a supersymmetric current again. So this is one of the results. And let me also discuss about the Reed-Rezai state. So which is often called the RR state. This Reed-Rezai state was proposed to generalize the Pfaffian Hall state, the Reed-Moore state. And on the boundary, so suppose that when you place this Reed-Rezai state in this bulk, on the edge, this edge physics can be described by the chiral part of this bosonic theories, which is a little bit sophisticated. It's a U1 compact boson theory and times ZK parafermion theories. And each theory has ZK global symmetries. And we will quotient this product theories by the diagonal subgroup. And here, there's one thing I would like to make comment. Sometimes, for certain values of K and M, this ZK symmetries, each individual ZK symmetry can be anomalous. But you can show that the diagonal subgroup is always non-anomalous. So we can safely quotient these product theories by the diagonal subgroup. All right, sorry. So the filling fraction in this case is given by K over K times M plus 2. So we can again work out the same exercise again. So we can apply this Jordan-Wigner transformation to this bosonic theories. And you can show that the fermionic theories become supersymmetric for special values of K, for K and M for instance, 2,1 and 4,1. And based on that observation, we can make a conjecture that actually this read-regized state becomes supersymmetric for when this k becomes even integers and m is given by 1. So in other words, when you place this read-regized state in the bulk with the special values of k and m, we expect to have a supersymmetric current on the boundaries. Indeed, recently, there was a proposal by condensed method theory people, those gentlemen, that this read-regized state with these values for k and m has an emergent supersymmetry on the boundaries, which is consistent to our observations. So it would be very interesting to prove that this RR state becomes supersymmetric for this for any value, any integer values for k, and m is given by 1. Right, so let me wrap things up. So let me finish my talk with the concluding remark. One of the most important questions we can address here is that, can you really experimentally realize these fractional quantum Hall systems? Well, I mean, it's a bit shame that I'm totally ignorant on the experiment related to this fractional quantum Hall system. Not only the fractional quantum Hall system, but any kinds of experiment, I'm totally ignorant on it. But even for that, even to me, it is quite non-trivial to realize some condensed method systems which has this non-abelian group. So I guess it's very difficult to find any condensed method system which realize this fractional quantum Hall state. However, at the same time, I'd like to remind you the following things. It is known as the Frankel-Catch constructions. So the G1 when you consider this Jordan-Wigner model, when with the label is given, where the label is given by 1, this Jordan-Wigner model can be also described as the Bojanic, the U1 rank of G model, which is defined on the root lattice of the group G. So one of the well-known example is SU2 level 1, which can be understood as a compact boson, a theory of the compact boson on a circle with special radius. In that case, I mean, the U1 can be promoted to the SU2. The same thing can happen for arbitrary group, actually, G. But the label is always given by 1. So in this case, so that implies that when you place the G1 Chern-Simons theory in the bulk, the physics can be shared by the rank G copies of U1 Chern-Simons theories. But in this case, we can introduce rank G by rank G Chern-Simons level matrix K. And this level Chern-Simons level matrix K should be given by the Cartan matrix of the group G. And when you look at the table again, there are 4 examples which has the level 1. So in this case, we have abelian descriptions. And in that case, I would say maybe there is a possibility to realize this fractional quantum Hall system experimentally. And that would be very interesting. All right, so that's all what I want to say today. And thank you for your listening. Thank you.
Okay, thank you very much. Okay, are there more questions?
Question?
Mm-hmm.
So the list of West-Wigner models that allows familiarization you showed, is it the full list?
Experimentally, but I guess quite robust. It's not a mathematical proof yet. I mean, there could be some other examples, but for certain values of the, for instance, in this case, you can see that there's an interesting relation between the rank and the label, such that n times k is always given by 12.
Right.
Yeah, this one also satisfies those conditions. So maybe it could be the full list
And the orbifold, do you, it cannot be larger than Z2 or?
That would be interesting. I'm not sure yet. Yeah, but I'm not sure. There could be some other example which can support the supersymmetry on the boundary, but that we search for this bosonic theories for rank is around 15 or 16. I don't remember the exact numbers, but sufficiently large rank. But maybe beyond that, there could be some other example.
I see. And you also require a simple group, not semi-simple.
Yes.
And is it possible that some semi-simple groups non-trivial?
Yeah, you certainly have such a possibility. When you consider some product theories, there could be some emergent symmetry, supersymmetry. But I haven't explored that possibility yet.
Okay, thanks.
Excuse me, related question I have. So under the level rank duality, SU and Chern-Simons gauge theory map to UN gauge group. So, but your list does not include the UN gauge group as a symmetry on as an example with supersymmetry on boundary.
Oh yeah, because I haven't searched for that case actually, because I want to focus on the case where G is simple.
I see.
Yeah, so I'm quite sure that this the corresponding the unitary case, there could be some example which can support the supersymmetry on the boundary.
So if I correctly remember, SU12 level 1 Chern-Simons gauge theory is dual to a U1 level 12, or I don't remember exactly, but I think it's dual to U1 level rank dual to U1 gauge theory. So if this is the case, so U1 gauge theory also can show supersymmetry on boundary.
Yeah, I would expect so, but I haven't studied.
I see. Thank you very much.
Thank you.
Okay, more questions?
I think there is some questions in the chatting room. How many supersymmetry do I expect for C equal to 11 theories? That's interesting questions. At least n equal 1. But so for these theories, I don't remember the details, but let me go back to the table. Where's the table? We are not sure yet, but I would say this one support n equal 1 supersymmetries, but the read, sorry, what happens? The read Regge state for, let me share the screen again. So I said, what happens? The read Regge state for the special values of K and M can support the supersymmetries. They can support n equal 2, at least. The reason is that in the NS vacuum, not only the supersymmetric current can appear, this primary, conformal primary can appear as a descendant. The conformal weight, the conformal primary of weight 1 also appears as a NS vacuum descendant, which play a role as the R-symmetric current. So for this example, we have such terms in NS partition functions. So we would expect that the corresponding supersymmetry will be n equal 2 at least.
In that case, actually, don't you need something like coefficient 2 in front of chi?
Oh, yeah, I mean, with the right coefficient.
Okay.
Yeah.
Okay, are there other questions? Okay, let me ask my question then. Yeah, so basically you were studying necessary conditions for supersymmetry, right?
Yes.
Do you have ideas about sufficient conditions, or actually actually checking if there is some supersymmetry?
Unfortunately, no. We try to compute, at least for the simplest case, we try to compute the OPE itself. But we realized that it's not easy to compute it at all, even for the rational conformal, even though this Westover-Witten model is rational conformal field theory. So we would like
also other papers which study supersymmetry, right? Like a paper by Johnson Freud.
Yes, yes.
Yeah. So can you comment on?
That part is a little dubious for me in a sense, because what they did is that they try to use. Let me use this notation. Oh wait. And I can use this. Okay. So in that case, they are. Am I right? So they try to consider this kind of relations. So on the left-hand side, we have a J functions, which is a SL2G invariant, which is the partition function of the monster CFT. And these monsters, J function can be, some cases, written as this form. There's a finite sum and product of two terms, each of which can be understood. There's a chi I can be understood as a conformal characters for rational CFT 1, and the other vectors chi tilde I will play a role as the characters for rational CFT 2. And what Johnson Frey did is that when these characters chosen as conformal character of the known supersymmetric rational conformal field theory, and this part is guaranteed to be supersymmetric. So that's the basic idea. So he tried to use these kind of relations to propose that certain bosonic theory can support the certain Westover-Witten model can have a supersymmetries, but it's rather mathematical. So beyond that, I couldn't follow his argument. So at least I can, I'm sure I can say this one. I can say that he didn't compute the OPE. Okay.
Okay, thank you. Okay, are there other questions or comments? Okay, in that case, let's thank Sungjay again.
Thank you.